What's a series? A sum, right? A sum of a list, a sum of a sequence. And what's the pressing question if we have a series, right? What's the pressing question? Yeah, and what does that mean? Does it converge? What does that mean? Yeah, when you add up all the terms together, do you actually get a number, right? Or does it just get really, really big, like bigger, just bigger and bigger? That would be, it diverges, right? So it converges means that when you sum all the values together, you actually get a number. That's the question we're asking. Okay, so to answer that question, we have a bunch of tools, right? We're building a toolbox of ways to analyze series for whether they sum up to a value, converge, or whether they do something else, like get really big or get really big negative, or just keep jumping around and never really sum up to a value. So I want you to talk to the person next to you. So we have to know our tools and have them at our fingertips when we come to any given series, right? So, and this toolbox is growing, so we have to file all these things away, what they mean, how to use them, and then know how to apply the right thing at the right situation. So let's just review. Why don't you talk to the person next to you? What's the headline for all of these? What's the headline? What's the big point behind each of these, so that we're just have these ready to go and ready to use. Go.
Geometric series. Given R value, given geometric sequence of R values, that's absolute value. Well, traditionally,
Okay, here we go. See how my headlines compare to yours, okay? So the first one, the divergence test. If the limit of the sequence doesn't go to 0, then the series diverges. So this is the whole idea that in order for a series to converge, so the flip side of it is, in order for a series to converge, what has to be true? In order for a series to converge, what has to be true? Don't just, I gotta get all this stuff down and you're not listening, right? So the whole point is so we keep reviewing it over and over and you're thinking and then it starts to stick. If you need to take notes, do it with a video later, okay? So we gotta just keep thinking through these ideas and reviewing these ideas over and over again. But if you're writing, you're probably not, writing frantically, then you're probably not thinking about it. All right, so what would have to be true if the series, in order for the series to converge? What would have to be true? I know Neil and Nick know. Yes, sir. Yeah, this limit of the sequence has to go to 0 for adding all those things up to add to a number. It should make sense, right? Where that sequence is going those numbers have to get super small so that when we add them all up, we get a finite number. So that means that if that limit doesn't go to 0, game over, end of story, right? Series diverges. And that's the first thing we always check for, because these other ones maybe take more work, and we don't want to do the work to, chisel away at the series when, we didn't have a limit that went to 0 in the first place, right? Okay, so the limit's got to go to 0. The limit of the sequence has to go to 0. So then when we add them all up, does that guarantee it'll converge? No, maybe not, right? So it's like now, if the limit of the sequence goes to 0, now we have a question. Like now it's like, here's where it's interesting. Will the series add up to a number or not? Okay. Geometric series. Geometric series converges when the R is between -1 and 1. And this is the one case where we proved what the sum is, like precisely what the sum is. A over 1 minus R. And what is R again? So what does it represent in the series? What does R represent in the geometric series? In terms of the terms. This is important for what we do today. Yeah?
R is like the value they multiply by each previous term to get the next term.
That's right. So our geometric series looks like this, right? So you see this and you think what, right? You see this and you think, tells us that it's this. So what's happening as we go from term to term? You multiply by r. And does that r change or does it stay the same? It stays the same. It's always multiplying by r. I'm trying to say times r, but for some reason I can't. So you always multiply by r to get the next term. Hold that thought, because this is a big idea that comes along with what we work on today. Okay? In a geometric series, you have this value r, and to get the next term, you always multiply by that r. So if that r is like a fraction, right? What happens if you keep multiplying by a fraction? That's what these numbers are, right? They're fractions. Keep multiplying by a fraction, you're going to keep taking that same percent. It's going to get smaller and smaller. And so then eventually that sequence will go to 0 and fast enough so that it sums up to a value, a over 1 minus r. Okay, p-series. P-series look like 1 over I to the p. And this diverges when p is less than or equal to 1, but converges for p greater than 1. And we showed this, right? We worked a lot on the harmonic series, and we looked at p-values like the square root, so we worked on a lot on this. So we're going to keep our lookout for p-series. Comparison test says that a series diverges if it's bigger than a series that diverges, that we know, right? And it converges if it's smaller than a series that converges. That's the comparison test. So we're comparing it to a known series. If we have one that diverges and ours is bigger than it, then ours diverges. If we have one that converges and the one we know we were working on is smaller than that, then it will converge. That's the headline there. Alternating series test. Says that an alternating series so the alternating series converges. When does it converge? If bi decreases to 0, right? So I think I kind of pair alternating series test and divergence test together, because the divergence test says, well, it's related to the idea that if the sequence goes to 0, then does the series converge or diverge? If the sequence goes to 0, does the series converge or diverge? Maybe, that's right. The jury is out, right? This is the necessary condition that the sequence go to 0, but it's like maybe, maybe not. Well, now, in the alternating series, if the sequence goes to 0, the positive part of the sequence goes to 0, and it alternates, then it converges, right? So that's not, but the alternating part takes away the maybe. The alternating part makes every other term negative, and this makes it converge every time, as long as your sequence goes to 0. Make sense? Okay, this is all review. Hopefully this is at least familiar. Ratio test. So the ratio test is looking at makes myself some room up here. Okay, the ratio test says that we make a new sequence, right? We make this new sequence, and what is it? It's the ratio of consecutive terms in our series, the ratio of consecutive terms. And we look at that sequence, and we analyze it for whether it converges or not. And so what is that about, right? So if I have a sequence, A1 plus A2 plus A3, AI. So here's a sequence going on and on and on, like this. What is AI plus 1 over AI? What is that? In effect, what is that? Do you remember what we said at the end of class this time? That ratio of AI plus 1 over AI. Anybody remember? It's what you'd multiply the AI times to get AI plus 1, right? So AI times this ratio, AI plus 1 over AI. So what is this? This is the multiplier to get the next term. But it's a sequence, right? It's a sequence of multipliers to always get to the next term. So what's that kind of like? Yeah, it's kind of like R in the geometric series, right? But in the geometric series, it stays the same. R stays the same. But in any series, that could change, right? So we're looking at the sequence of multipliers. It's kind of like this is R1, R2, R3. And that's what this is. It's a sequence of multipliers. So if that sequence of multipliers converges to something less than 1, then what's happening to our series? It's like becoming what? Geometric with that R value, right? So if that sequence is heading towards, say, 1/4, then it's like this series is becoming geometric with an R of 1/4 in the long run. So would that converge or diverge? Converge, because R values between -1 and 1 make for a series that converges. All right, so that's what this ratio test is doing. It's like looking at the sequence of R values, right? The sequence of multipliers from one term to the next, and saying, does that sequence indicate that this thing is becoming like a geometric series that diverges or converges? So we're kind of testing it to see if it like is becoming a geometric series. So that's what this does. Okay. And so let's do examples of that. Any questions on the toolbox? Okay, so there's this memorizing the facts and then being able to reason with them, both, and you got to have both, right? To succeed at this, you have to have the facts down. That's why we practice this. But then there's also this, you have to kind of bring the facts together and make conclusions, right? You have to reason with them to analyze these. So it's both. Okay, first example. So we're going to use the ratio test to see what happens with this series. So what we're going to do, we're going to form this ratio, the I plus first term to the ith term. And you can use I, you can use j, you can use k, it doesn't matter. So I'll just, in this first one, I'll use I. So the I, what is the I plus first term of this? -3 to the I plus 1 over I plus 1 cubed. So anywhere you have your index, it's now the next one. The next one, or adding 1 to your index. And that's going to be what? Divided by the ith term. So what's the ith term of this? -3 to the I over I cubed. So we're looking at the absolute value of that ratio. So that's that ratio. This is the I plus 1 over AI. Absolute value. And how do you divide fractions? Multiply by the reciprocal. We're going to multiply by the reciprocal of the ith term. So that's I cubed over -3 to the I. From here on out, you can start on this. You can start with this step, right? So you can do instead of starting with this fraction of fractions, start out with a product of fractions, where you do the I plus first term times the reciprocal of the ith term, because that is what this is. Okay, so you can just start with this. Okay, and then now we're gonna simplify what's inside the absolute value there. We gotta know exponents. So what does this mean? It means -3 multiplied together this many times. So does this, negative 3. So where do we have more negative 3's multiplied together? Top or bottom? How many more do we have in the top? One more negative 3. So that leaves just one negative 3. Got one more negative 3 in the top than we do the bottom. And then I got I cubed. So now we got to reach back a week or two. We're analyzing the sequence now, the sequence of terms. And we want to say as I gets big, what does that sequence do? So we've got, this is our rational function, right? This is where we compare the degrees of the numerator and denominator. And how do they compare? So so we're asking what's the limit of this, or what happens to this as I gets big? Goes to 1, right? 1. Okay, so we got I cubed up here, I cubed down here. Those are the leading terms. So I cubed over I cubed, take the ratio, so that goes to 1, leaving us negative 3. So the limit of this is 3. So what was this thing again? What was this ratio again? What does it represent in our series? The ratio is the sequence of what? Starts with M. Sequence of multipliers. Multipliers to get to the next term. Remember this? Sequence of multipliers to get to the next term. And that's those multipliers are kind of like what? Values of r in the geometric series, right? But it's just a changing value of r. So the multipliers are changing, but in the long run, they become 3. So to get the next term, it's like in the long run, in the next term, we always multiply by 3 to get the next term. That's what that means. The sequence is going to 3. Therefore, what about this series? Diverges. Because it's like becoming a geometric series with an r value of 3. That's what this is telling us. It's like turning into a geometric series in the long run where the r value is 3. That means you're always multiplying by 3 to get the next one. And when you add those together, it's going to blow up, right? Okay, questions on this example? So we find out what the limit of this sequence of multipliers does. And this is like we're trying to see what it does. Does it turn into a geometric series? And if so, what is the r value that it's turning in, becoming? Any questions? Okay, next one. Okay, see how far you can get on this one. Remember, you can start with the product. So you can start with AI plus 1 times the reciprocal of AI. Flip it over. Where's Austin? Austin. Did you get started on this one?
Yes.
Tell me what you did first.
So for the first fraction, I just did -1 to the I plus 1
Okay.
times 7, and then parentheses I plus 1 squared
Okay.
over I plus 1 in parentheses cubed plus 4, and then multiplied by I to just the fraction flipped. So
Okay, agree with what he said? So now we gotta simplify this. And that means like looking at like combining things that are like. So we got the -1 to the I plus 1 over -1 to the I. So you have one more -1 in the top than you do in the bottom, right? Okay. And then we're going to look at seven I plus 1 squared over 7I squared. And I cubed plus 4 over I plus 1 cubed plus 4. And this, so we have to find the limit of this. Agree with what I wrote? Are we good? Everything look good? Okay, so what's the limit of this? Some people are saying the 1. So 7's go away. So we can kind of chunk it up, right? We can kind of the limit of these things that are like. So what's the limit of this right here? I plus 1 squared over I squared. 1, because you have the same, right? Same power. And it would just be the coefficient, the ratio of the coefficients. What about this? I cubed and I cubed. Again, 1, right? So this goes to 1. This goes to 1. Therefore, the limit is 1. And as you see right here, there's no, sorry, it's not equal. That's right. So goes to 1 as I goes to infinity. So no conclusion. So what does that mean? We have to reach back into the toolbox and do something else, right? So the ratio test is not helping us here. The multiplier is becoming like 1, and that's an open case, right? That's jury is still out. It may converge, it may not. So we go back to this and we say, what other tool in our toolbox might be able to help us with this? Some people are saying alternating series test. So the alternating series test says that color in here. Alternating series test says look at the positive part of the series. 7I squared over I cubed plus 4. What does that do as I increases? 7I squared over I cubed goes to 0. And it alternates, right? So we've got a sequence that goes to 0, and we have it alternates. Conclusion? Series converges by alternating series test. Okay, but then we can ask another question, right? What question could we ask in addition to this? Yeah, does it converge absolutely or conditionally? Does it converge absolutely or conditionally? And so how do we tell that? Then we look at this series, right? The all positive series. We know that the sequence goes to 0. Combine it with the alternating effect, and you got a series that converges by the alternating series test. But now we look at the all positive version of it. Does that go to 0? Does that converge or not? What do you think? So we have to reach into the toolbox and see what tools do we have to see if 7I squared over I cubed plus 4 is going to converge or not. So is it geometric? Is it a p-series? Similar. So can we compare it to a p-series? What p-series would we compare this to? We got I squared and I cubed. So this sequence, and 1 over I. So 1 over I, does it converge or diverge? Diverges. Is this bigger or smaller than that? Well, we made both the numerator and the denominator bigger. So you can't really say that it's always bigger, okay? So instead, we can use that other kind of comparison. Remember this? Limit comparison, where we say this thing becomes like, in the long run, like 7 over I, doesn't it? When I gets really big, it's essentially, we get 7I squared over I cubed, which is like 7 over I, which diverges. Because it's like the alternating series, or the harmonic series. And then we come back and we say, okay, so therefore, is the series conditionally, does it converge conditionally or absolutely? Right, so without the alternating effect, it diverges, right? Without the alternating effect, it diverges because it's essentially like a harmonic series. So it needs that alternating to get it to converge. That's a conditional convergence. Okay, so ratio test yield no conclusion. Alternating series test told it that it can converged, but then we check for absolute convergence, and we see that it's like without the alternating, it's like the harmonic series, which does not converge, so it's conditionally converges because it needs that alternating. It needs this in order to converge. Without it, it doesn't. Questions on that example? Okay, here we go. You start it, I'll call on someone in a bit. Okay, where's Joanna? Joanna here?
I think you call her name every time she drops.
She dropped. Very good. Okay. Jordan, you're up. Did you get started on this?
Yes.
Tell me.
So -1 parentheses k plus 1,
Mm-hmm.
and then 2 k plus 1, off, and then below it parentheses k plus 1 factorial,
Mm-hmm.
and then multiply k factorial, -1 to the k,
Mm-hmm.
and 2 to the k, and then the -1k and -1k will can be canceled out, so then it'll be -1. Same with the 2k and the 2k, so it'd be 2 on top.
Okay, so you're saying 2 to the k plus 1 over 2 to the k means one more 2 on the top than on the bottom? All right, and let's just review. We talked about factorial in a little bit here. So let's just review what those are. So am I good? This is what you put?
Yeah, I think I might have messed up with factorial.
Okay, so that's what we're going to take care of right now. So how would you describe what k factorial is? K factorial is? Remember what you do with k factorial? Neil and Nick? Yes, sir.
It would be k times k minus 1 times k minus 2.
Yeah, so you always start with the number that's the factorial, and you multiply by the number 1 less, and then 1 less than that, continuing that way until you reach 1. A 0 would not be good, right? You don't want to go to 0, because then what would happen? Every factorial will be 0. So we got to make sure we stop at 1. Stop at 1. Okay, and so then what would k plus 1 factorial be? Start with k plus 1, and then times 1 less than that, times, and then suddenly we see, what do we see? What am I writing now? Starting here. I'm writing out k factorial again. See that? Every factorial has all the lower factorials as a factor of it, right? They're included. So now I have k factorial over k plus 1 factorial. What would that amount to?
Just be 2 over k plus 1 then.
Right. So notice this is all k factorial. This is equal to k factorial. So when you take k factorial over k plus 1 factorial, you're left with just the k plus 1 remains, because k factorial is like the rest of k plus 1 factorial, and that will cancel out with the k factorial on the top. Agree with this? Everyone, makes sense? Okay, as k gets big, what's the limit? Negative 2 over k plus 1. That's the easy, right? That's the easy sequence. Goes to 0. Conclusion? Yeah, this converges absolutely according to the ratio test. And so we could say, what about this series? What can we say about this series? But what did this number tell us about the series? What did this number tell us about the series? Besides the conclusion of converges absolutely, what kind of added information do we have about the series, knowing that this limit of these ratios was 0? Yes, sir. Okay. Yep. That's what converges mean. But more specifically, what specifically does this 0 mean? What's that? What does that 0 tell us about this series? Yep, that's what converges means. But more specifically, tell me, Chance.
Geometric.
Is this a geometric series?
Becoming like
It's becoming like a geometric series with where r is heading to 0, right? So I'm repeating this over and over because it's important, so don't tune it out. This is like a sequence of multipliers, right, on the terms. So this is kind of like the r value in a geometric series, but it changes, right? It changes from term to term. So we're looking at in the long run, what do those multipliers do? Like the r value, right? So if it becomes something less than 1, then we've got, if L is less, if the limit's less than 1, it's like becoming a geometric series with that particular r value. In this case, 0. Okay. Another example. Oh, so while I'm thinking about it, so the next homework opens today at 3, and after this class, you'll be ready to work on numbers 1 through 10. Then after Friday and Monday's class, you'll be ready to work on the rest. So there's nothing to stop you from keeping going, but just 1 through 10 is you'll have enough to go do today. All right, let's see what happens on this one. Okay, so when you get to the second step, we got k plus 2 factorial over k. So first of all, did I make a mistake? I can make a mistake. Do you agree with what I did? Yeah, I got one nod, 2 nods.
This is unsimplified, right?
Sure, yeah, this is still going. All right, so what's k plus 2 factorial over k plus 1 factorial? That just says a k plus 2 in the top, right? And then we don't have one more 5 in the bottom because you should have 5 times 3 to the quantity k plus 1. That makes 3k plus 3. So how many more 5s are we multiplying together in the denominator? We have 3 more 5s. Okay, limit. Negative 1 times k plus 2 over 5 cubed. What happens to this ratio as k gets big? Gets big, right? Conclusion? Diverges by ratio test. Or in other words, the multiplier, the sequence of multipliers from one term to the next, those multipliers keep growing and growing and growing. So it's going to blow up when you try to add it all together. Questions on this one? So the key thing to watch here is this is not 5 to the 3k plus 1, ends up being 5 to the 3k plus 3. That was the key fact here. All right, let's do the last one. Can I erase? Are we good? Okay, how many more 6s do we have in the top than the bottom? 1. How many more 3s do we have in the bottom than the top? 2 more, right? So it's 2 to the times j plus 1 would be 3 to the 2j plus 2. Would be 2 more than this, so 3 squared. Limit of these cubed terms, the limit's going to be 1. So I don't want to rewrite the orange stuff. It's the orange stuff. And that limit is going to be, orange stuff goes to 1. Therefore, the limit goes to 6/9 or 2/3. Conclusion? Series converges, right? Converges because the ratio test converges absolutely. And what's the meaning of the 2/3 number? Tell the person next to you. What's the meaning of the number 2/3 relative to that series? What does the 2/3 tell us about that series?